Всем привет. Так,
Hello, everyone.
давайте тогда начнем. Меня зовут Александр Ланцов, я приветствую
Let's start. I am Alexander Lantsov.
модели памяти.
I will talk about
Познакомимся.
memory model evolution.
Так, оп. Да, давайте сначала познакомимся.
So let me introduce myself. I work in a MIR platform, which develops a MIR payment system, fast payment system, and you can learn about me, what I have done before. So we're going to look into many articles and examples. You can learn them on GitHub using this link. So memory model, there are two words, but there is a lot of essence, a lot of meaning, depending on who is discussing. If you're a hardware developer, you would think about memory model in your architecture, x86. If you are an application developer, you would think about how the model memory is built into your language. If you are a hardcore system programmer, you have your own memory model and it works using your own rules. If you are doing in compilations, you would say that LLVM has its own memory model. And if you are a researcher, you would say that that is interesting. However, some academic work is more interesting. Thinking of new academic works, trying to expand the meaning of this terminology. So, memory model, it depends on the context. Who is thinking about this? And the goal of this presentation is to answer why it's so complicated. So, in order to grasp this, let me make a plan. We would answer how everything has started. Everything started with hardware, when there was a multiprocessor system first appeared, and how the memory models appeared in software, in programming languages, because this was mainstream for Java and it has been improved later. We'll talk about academic works, why we're researching in this area, and what are they trying to find, people who are doing this. And at the end, you may think what to do after what we learned today, and I will try to answer this. So let's start where it all comes from. First, articles and multi-processor, multi-nucleus systems, and the mainstream systems. First multiprocessor appeared before. In the beginning of 1970s, there was a lot of systems that were made of several processors that were working at the same time. And all the developers, they had some problem. How developers could be granted guarantees if there are several processors, how to make the rules. Because you can make your own rules, but each time when you change hardware, you would have to make it from scratch. And then there is sequential consistency, also known as SC, a Lamport article of 1979, that if you have one processor, how to make of a multiprocessor system which works correctly. And this work has introduced sequential consistency, which has some difficult definition unless you understand it formally. So let me explain sequential consistency informally. If we have several executors, processors, or flows, and you say that only one executor works. One flow it performs several number of operations, then you switch into a different flow and making operations from that flow. So at each time you have one flow working. Now we are in the hardware era, so I'm going to use terminology executor, and then I'm going to talk about flows. So example, what's the idea of sequential consistency? We have two fixed areas in the memory with their variables A and B, and initially they had 0. First executor performs two commands moving A and B variables, and then the second executor takes the value of A and B in R1 and R2 register. R2 equals 2 and R1 equals 0. That means the second executor has seen that we've written something in B and hasn't written something in A, although it was vice versa. And sequential consistency mental model says that in each moment of time only one executor is working. So let's imagine an execution landscape. So let's suppose that A equals 1 and then B equals 2. Then we would go to the second executor flow, first reading B, and then reading BA variable. We can also have a different execution journey. It could be second command from the first, and then we perform the last command from the first variable. So what kind of executor we are using and what kind of command we are executing? This can be done combinatorily. We can also do smartly, first performing A equals 1, or to perform the B variable. Sequential consistency semantics is most convenient in the correctness of multi-flow programs. However, there is one problem. Sequential consistency is not free. What's the problem? In order to implement it effectively as to hardware, we need to violate this model as to the speed of processors and memory. So we need to weaken this model. And how can we weaken this model? We can do it differently. We can return from where we started, that each processor has its custom architecture, custom rules to work with multi-flows. But the researchers were able to answer this question. Article of 1990, weak ordering and new definition. It's sequential consistency, data race free. So if you don't have certain data rift, then it works in data race. Free. So it depends on how your code behaves as to different variants. So if there are no race, it's all good. So in order not to have race, hardware provides some magic operations. such as synchronization operations, as you know them, as barriers. So between different operations of different flows, you may guarantee that there is no race. And race is when you have two competing operations from where one is recording. So if you cannot use it as primitive signalization, then everything works unclear. But if you've written everything in order, then there is sequential consistency, a contract between software and hardware as to the data race free. So if everything is done according to the rules, it would work well. The most well-known architecture is x86. Some history in 1996 there was Pentium Pro, and although at that time there were no multi-nucleus systems, but even at that time you could collect a multi-system. There was an opportunity for multi-core system, and by 1996 there was a question: how can we use this? And there was an explanation on some forums and mail lists. In 2005 there was Pentium D, which was quite cheap multi-core processor, and when you can have multi-processor system. But what's more interesting, only in 2007 there was first explanation how the memory model is structured into Intel. So the developers did not want to give too many guarantees, because if you give too many guarantees, then you would remove some potential ways of optimizing your hardware. As I said, sequential consistency costs quite a lot, and even if you give strict model of memory, you will have to abide by it. So developers made quite a loose model, and that model was not correct. It does not reflect real hardware. There were some outcomes that were prohibited, and so this memory model was incorrect. And only in 2009 there was a formal specification which was fully correct, which has described how Intel works in case of races. And you see there is a big gap between potential programming in multi-processor system and specification, how it all works. A lot of time has passed. Let me describe some mental model. Mental model means we don't know how it works inside of the hardware, but there is a simplified model which outcomes are followed in this model. So we have a single memory, we have several cores, and each of them is making their own threads. So they are reading from the memory, so each thread reads a value from the memory using specific address. But when writing to memory, they would write to some buffer, which is called star buffer, and after some time they are getting into the main memory. And when processor reads from the memory, it turns first to the stack buffer 2, and such stack buffer is available for each processor. They have a consequence from recording. First example is passing, message passing. We have A and B variables. In A we have 1, in B we have 2, and in the other thread we were reading A, reading B, and then reading B, A. So if we have written something into B, we remember that we haven't written into A, but sequential consistency says it's impossible. X86 also says no, because we have only reading operation and writing operation. So if your value goes into star buffer and some star buffer gets into the memory, then all the values are also in the memory. So the answer is the same as in sequential consistency semantics. Another example where we can show the differences of sequential consistency from x86. We also have here A and B variables, but in the first thread we're writing A1 and then reading B, and in the other thread we do symmetrically opposite. We write B, we write 1 into B. So R2 and R1, can we see 0? Sequential consistency says no, because all operations. So first operation would be give 1 or 2 to B or A. And at x86, this is possible because using our mental model, each of the thread has made its record into store buffer, and there are zeros in those values. There is also ARM and there is PowerPC. I'm not going to go into the depths of the memory models. I'm just giving you some simplified diagrams, how they behave. I'm going to show you an example that in those architecture, outcomes are possible which were not possible at x86. The same message passing. We've written zeros into A and B. A is 1, B is 2, and reading them in reverse order. So in B something is written, in A something is not written, and then sequential consistency and x86 say no. But in Power and ARM, these outcomes are possible, because you may not see these processes at x86. So if you are going to convert your programs from x86, the outcomes may appear since you've migrated to different architecture. And they have some coherency. Coherency means that all traces of one value which we see in the memory, they are done in a coherent global order. For example, coherency definition. So what's the idea of coherency? We have only one variable, x, with 0. We have 4 threads. In x we write 1, in second thread we write 2, and we're trying to answer the question whether this outcome is possible. It looks complicated. R11, R22, R32, R41. So the idea is that in the third thread we've written x1 and then 2, and in thread 4 it's 3 first and 4 second. So the answer, if we write it in assembler, the answer is no. because of this guarantee of coherency. Now we move to programming languages, because we're looking in the same coherency. Let's try the same example using not assembler, but a different language, such as Java. We are calling x variable, we're writing x1, x2, and then we are reading them 2 times in a row. So the third thread, we write first 3, then 4. So if we write this in assembly, the answer is no. But in any programming language where there is multi-thread, it's possible. Because the functions are much wider than in hardware. So you cannot use the architecture which is available because memory model is much weaker than what is available in hardware. So we need to use the programming languages correctly. How they have appeared into the programming languages, the memory models. We have sequential consistency data race 3, which was first used for the hardware developers. There was a contract between hardware engineers and software. So there should be a contract between software and hardware as we implement our programming language, compilers, and those that are going to use this, writing some programs and software for these programming languages. And sequential consistency principle for data race 3 is ideally suitable. So we have some synchronizing operations, not to specify the hardware, but to specify the language. So we're writing the program in such a way that there will be no race. And if there is no race, then the program behaves as to the model, memory model, sequentially consistent. It's the most simple model. So let's look into Java. In Java, there was a first attempt to make a memory model. It's quite interesting. As to the history, the first memory model has appeared into the first Java specification in 1986, and this principle has not been used yet. Although there is volatile, it hasn't used sequential consistency data race 3. There was no definition of synchronized operations definition. So volatile was a special word that they would make the most pressing value of this variable. So that was a feature. Any Java specialist knows this. We have x value, we have written 0, and then we have a flag for volatile specifications. In one thread we write x definition and giving a flag, and then we read x in there is no happens before. So we have coherent reading of the record through volatile. And in the first memory model, since different variables were not given volatile, we could not guarantee that it would work. So that was a fatal flaw of first Java model, and it was corrected in 2004 when people understood that they should use sequential consistency data race 3, and they have determined specific synchronized operations such as reading connection to the thread. Then when you use synchronized operations, there are no race. Using happens before, we have special semantic for final fields. And using happens before, we guarantee that there are no races and everything works well. But since Java positions itself as a secure language, it tried to answer how the program would behave if we do have races in our program. So in Java, there is a semantic for race programs. And that's why there are all these problems with memory model in Java. There are a huge number of articles about it. So let me talk through, give you some examples from these articles. Let's look at this program. We have x equals 0. We have several threads. First thread, x equals 1. Second, x equals 2. Third is x we're reading twice. And let me ask a question, whether invariant R1 equals R2. Try to answer this question.
Yes,
the answer is simple. Of course, it's no, because these variables. First of all, there is no volatile specification because there is a lot of races. Even if it would have volatile specificator, we could not do the reading because the operations we would see in a different order. So the answer is simple, no. R1 does not equal R2. It does not guarantee this. So let's make our program more complex. Let's add intermediary operations in the third thread. We enter x, which equals R1, and then we make writing R2 equals x. So is R1 equals R2? Same problem. Even volatile specificator does not guarantee, because the answer is no. So when we add some blockings on A and blockings on B in a different thread, so blockings are on different objects. We have third thread. We are taking blocking both for A and for B objects. So is it true that R1 equals R2? That is more complex question. The problem is that since we have blocking operations on two different objects in thread 2 and thread 3, they are competing, and we have a race in our program, and Java determines semantic for programs with races. It's quite difficult to argue. So Java showed that it does not guarantee that R1 equals R2. It sounds strange because we've done some lockings, but no one can compete and change. But as to the memory model, R1 doesn't equal R2. So let's go back to our modified program, and let's take this intermediary operations, and x equals R1. So invariant, is it true R1 equals R1 equals R2? In this case, the answer is yes, R1 equals R2. So what's the biggest problem from the memory model? One of type of this optimization is in its name. that compiler uses records that are not needed. So compiler says, can I throw away x equals r1? So it looks like this is we can skip it. And the common sense says that it's a basic optimization, but from the memory model, if we remove this record, then we move one array into the other array. And if we remove this line, we would have a possible outcome where R1 does not equal R2. And all the other problems of Java are from here, with programs with locks. A different example, a ticket on OpenGK. What's the idea? There is power C, there is a formal model, and you can launch some formal verificator. And if we take current realization,
then it'll say that those volatiles that have been implemented in OpenGK, they're done incorrectly because they're not used correctly. So it makes the writing into volatile much harder. But in terms of reality, not a single PowerPC piece of hardware behaves exactly according to the description model. And in terms of reality, this operation makes no sense. So in terms of the memory model, we need to make writing into volatile memory hard, but in terms of practical experience, it's not going to fix the program. It'll just put it all in our performance. So as I said, there's a problem between how the formal model is different from the one implemented in our Java machine. And there's another problem. In Java, there are intermediate semantics, var handles. They ruin the consistency in arrays-free structure. So you'll make everything correctly, theoretically speaking, but the program will not behave according to the existing semantics. Okay, we've discussed Java, but there are other languages, such as C++, for instance. Let's consider it. It got memory model in 2011. It's also depends on consistent dependency arrays-free, but you need to use it explicitly, std atomic. If you have arrays not on atomic, then you have a defined behavior. Well, in theory, that could result in positive things. So you would be able to write some arrays detector. So actually, it's not as bad as one would think. C++ has intermediate ordering. So it looks like what we have in Java. So using these orderings, you can order access to memory according to the model of this language. But unfortunately, C++ has the same problem as Java. There's another paper that I'm referring to. So what is the idea of this example? We have two variables, x and y. They're wrapped in atomic, they're regular integers. We have thread 1. This operation looks a little bit complex, but actually it's quite simple. We check the value of the variable x in relaxed ordering, and check if it's equal to unity or not. If it's equal to 1, we assign the value of 1 to the variable y. And we do the same thing in another thread. We read the value of the variable y into like semantic, check if it's so, and then if so, we assign the value of 1. So is it possible that x would be equal to 1 and y would be equal to 1 as well? So it looks strange, but in fact, in terms of the C++ memory model, this outcome is quite well known. So it's quite possible in the C++ memory model. You shouldn't have written anything in theory, but nevertheless, it has been written. Okay, let's make our example a bit more complex. Let's modify our program. So we have the variable a, it doesn't have atomic, nothing like that. The second thread is exactly the same as in the previous example. We've checked the value of the variable y. If y equals unity, we assign x equals 1. Then in the second thread, we do it in the intermediate level. First, we check the value of the variable x. If it's so equal to 1, then we check the value of a, and if only if a is equal to 1, then we assign 1 to y. And the third thread is just we assign 1 to a. Again, I'm not going to go into details, right? But it's shown in the paper that from the point of view of the C++ memory model, the only allowable outcome here is x equals 0 and y equals 0. But there are all sorts of optimizations, some simple, some complex. I'll offer you an example of some exotic optimization because it'll just illustrate an example. In fact, real-life examples take more time, but nevertheless, let me show you this example. It's called sequentialization. We have two threads, and let's just execute thread 1 and then thread 2. Why not? Let's do this sequentialization of thread 1 and thread 2. That's we will pass the assignment of unity to A into thread 1. Unfortunately, this will make our problem into a situation similar to the first example, like out of thin air. So using some optimization, we'll have broken our program, which means that you can't apply this optimization in terms of common sense. You do want to do that. Same problems as in Java. We violate formally the memory model, but in reality, just makes the system work faster. So one might think that these are old languages, and maybe they thought of some solution in the new language, such as Rust. What do you think? Well, Rust developers were aware of the memory model, so therefore they just said that Rust does not yet have a defined memory model. Everything is just as clean as in C++. You have atomics, and everything would work fine. Also, we have the concept of ownership, so there's only one owner of an object, so we shouldn't have any race conditions there. So everything looks quite well, but nevertheless, if you violate these rules, you'll still go bypass the borrow checker, and you'll make some competitive record via unsaved, and you'll get into the undefined behavior problem. There's also an interesting problematic. As you know, Rust is actively trying to be used in the Linux kernel. There are some certain things such as control dependencies there, and you get into an interesting situation. Rust doesn't have a formal memory model, but in addition to that, you need to make it so that its memory model should be friends with the memory model of the Linux kernel. well, it would be interesting to see how they go out of this. Also, there's Golang, and in Golang, they just tell you, don't be clever. If you don't, if you try to do something that's not available, just forget about it. Nevertheless, they have. Well, as to the race conditions, informally, they exist, and either that leads to stops the race detector, or the read operation will return some value. But at least outer values are not allowed. Some compiling are not allowed. Compiler optimization method is not allowed. Out of thin air methods are not allowed. So that's why we're guaranteeing security, but at the expense of optimization potential. Also, developers decided there will be competition through coordination rather than via shared data. So an approach has been adopted that is quite different. So we've talked about some mainstream languages. We understood that all of them have some problems with the model memories. So let's talk about the development of memory models. As I said, in the current models, there are some similarities. They all use sequential data race free principles, but unfortunately, either they don't have guarantees in the case of race conditions, or if we do some races in Java, we have some problems with theory. More than that, in those languages that offer us guarantee in case of race conditions, these guarantees do not come for free. They are implemented at the expense of some optimization in your code. So it's all clear. But some people have not been happy about that. For instance, the author of this paper was not happy. What they were unhappy about in particular. They said, so if you've written the program correctly, then okay, everything's fine, everything was within classic semantics. But if you've run into a race condition, all your program is down. You need to think about it globally, and it's very hard. Let me show you several examples. Well, first, consider an example of C++. So you've opened code in IDE, and look what you're doing in your thread. You assign A plus 1 to B, and you see that there are no other operations with B array. You would expect that a certain invariant is observed. For instance, B equals A plus 10, because we've done it just once, so we haven't changed anything. Everything should work. It would seem this way, but if we have a race condition, everything behaves quite differently. Imagine we have a regular variable C, and we have another thread. So we assign 1 to C. And in addition to that, in thread 0, we assign A plus 10 to C. This is a different variable. It doesn't have direct relevance to A or B. And then the system says, we've calculated A plus 10 twice, so why would we do that? Let's replace and calculate A plus 10, and then assign this value, T, to C and B. And then it's only a short way to a disaster, because the compiler says, so okay, I assign P and you have T, so my register. So why do I not put B equals C? And then everything breaks down. We have written the value of C into B, and the invariant breaks apart. So we can say that we've hurt ourselves. We've created a race condition, and anything can happen. But this example is about something different. It's about you not being able to locally understand how your program will behave. Also, imagine we have class C that includes a variable x, integer variable x, and so we do what's written on the slide, and it's guaranteed that we don't do anything with A. But what can we say about what's happening? We will have to say that A equals 42 because there are no other operations. But again, it's easily broken. How? Let's introduce an intermediate variable, another global variable that has a reference to another object, not the one that we defined in thread 0. And in another thread, we work with this global object. For instance, we assign the value of 7 to global X. And in the other thread, we work with the same variable. But the compiler decides to reorder these transactions because they're not connected to one another, and we get that our invariant breaks apart. So in the case of a race condition, in Java, we lose the ability to consider this. So the authors of this book decided they're not happy about that, and they decided to work in a different programming language, OCaml. It's a bit exotic, but nevertheless, it's used by some people, especially in the US. In OCaml, a global runtime lock existed for a long time, has existed. It's not an interpretable language, but they tried to get rid of the global runtime lock, which they did in 2022. How they did that? Just like in Java, they defined certain memory access operations, atomic and non-atomic, just like there are volatile and non-volatile operations in Java. And they decided to use the principle of local DRF. What's in it? What's it about? It's about the result of reading X not depending on their existing race condition on another variable. So what's another variable means? It's quite difficult to explain. It's about the OCaml memory model. But there are some corollaries there. So the reading in a single thread from A will return the same value if there's no competing record. There's no out of thin air. It's good, but unfortunately it doesn't come for free. It comes at the expense of banning certain operations, so optimizations, such as local store reordering. It affects the performance, but they ran the calculation on Camel, and they believed that it wasn't too important for them. So maybe there are some more exciting things, but of course we want everything immediately. So we come to this thing called promising semantics. It's being actively developed. Some new versions are being released. It's a formal operational model. It describes your program from the viewpoint of an abstract machine. The abstract machine is answering the question of which situations are possible. It's written in some modifiable programming language. So what do the authors want to do here? The authors want to build a model that doesn't have out of thin air, that don't have any restrictions for optimizations, and they want to make it so that you shouldn't get undefined behavior in race conditions. So one would think that this is the perfect situation, but unfortunately there's one but. This description, the description of this memory model in the abstract machine, I think that would be too heavy for an application developer. One should come up with something simpler so as it would be easier to write programs. So it's an academic work, but quite promising. Not quite promising in my opinion. So we've looked at the evolution of memory models. We started with hardware with the first papers and gradually moved to the programming languages. And then we arrived at the conclusion that it's with the formal memory models, most programming languages have some problems. And every programming language finds its own way how to solve these problems. So you should understand the approach adopted in your preferred programming language. If you don't do that, you may run into a situation that your program will stop working. Also, we've learned that race conditions are still a bad thing because, as you see, bugs happen everywhere. Bugs happen in the specification and the hardware implementations, in compilers, and we, as application developers, also write programs with bugs. So race conditions should be avoided. And the final thing, how to live on. One would think, what makes the bumblebee relevant here? How would you think?
Ну да, шмель просто...
Oh, yes, yes. The bumblebee. There was this fable that the bumblebee can't theoretically fly, but they still fly because they don't know that they shouldn't be able to. Actually, it's indeed a fable. It's just that the early stage aerodynamic models could not explain how a bumblebee can fly, but later they developed the theory to the extent that it explained the theory why a bumblebee flies. So that brings me to the end. Thank you very much for your attention. Thank you very much, Sasha. Dear friends, please assess or evaluate this presentation using this QR code. And while you're doing that, I would like to talk a bit about your questions to Sasha. You won't have more than a few minutes for that, but for those who still have questions and don't have enough time, we suggest that you move to the lobby. And those who will have asked the best question of Sasha will get the book. Thank you very much. An excellent presentation. I have a question. Of all the languages that you considered, which one is perhaps the most deterministic execution trace, most best reproducible working with threads? Ordering everything as consistently as one. So actually, the answer is quite simple. Where you don't have multi-threaded things, then it works very well. Unfortunately, I won't be able to give you a positive answer because, as I've shown, every language has a problem, and every language has some potential approaches to solve it. There are other languages, such as Erlang, for instance. It works absolutely different. It's all about communication between messages, and it all depends on your energy, what you'll choose. As I've shown here, so guarantees against race conditions cost something, and that depends on you, what you want to use in your target project. Sasha, thank you for your presentation. I have two small questions. First, you showed a new model that's only being built and semantics. Has anybody already tried it in some popular programming languages? Maybe there are results, maybe something about overhead. Maybe you've already done something yourself in this one. So there are languages that use what? This new memory model that you showed, semantic, I mean. Well, it's academic. Unfortunately, there are no application languages. The freshest language for which we have some solutions, that's OCaml, it's local graph. Local semantic is still actively developed, is being actively developed because there are some theoretical approaches described there, but there's still a way to go for this to be usable in application development. And the last question, who lost the money? What's the reason for the presentation? Who lost the money? Why did you get the idea of making this presentation? I've already run a certain number of presentations on multi-threadedness, and I just encountered the statement that academics say, so memory models are broken in Java, so we decided to, understand what it's all about. I have a couple of questions. Hello, thank you for your presentation. I'd like to ask you if you could take the microphone. Does it work okay now? Yeah, okay, good. Of late, a lot of attention has been paid to quantum computers, and I'd like to ask, how do you think the quantum computers, their memory models at the hardware level, are the same as for traditional software, or everything is much worse there because qubits, are more sophisticated than bits? It's a very creative question. Thank you. Look, when we're discussing memory models, everything is determined. There are programming languages that work to certain rules. The quantum world is, for me, are there such a thing as threads? Because there are some computations made there on a quantum level, absolutely different. I'm not even sure if the memory models that we've discussed today are applicable to that one. I think that could be a very good idea for a presentation. Thank you. Thank you very much for your presentation. Exciting as always, but I would like to have some clarity on the following point. In all the main examples, it was about working with a global variable in different threads. Nevertheless, there are situations where we can't predict the order of execution of these throws. When you get into a situation like this, saying unequivocally that we need to work with certain barriers, and that should be known and understood by the programmer. In that case, I'd like to have it clarified. You mentioned that one way or the other, you know Erlang. Do you know other? And the subset, the Spark language, that is also about provable verifiability. You know, I've heard these names, these titles, but I haven't worked with them myself. Because because the language, there are some interesting models there. So I will familiarize. Thank you for your comment. I think that maybe we'll have the time to take the last question from this person. Hello, thank you for your presentation. My question is like this. Can modern statistic analyzers fully detect the presence of race conditions in the code? And how about this in Python? Well, unfortunately, the answer to your question is more likely negative because there are indeed statistical analyzers that detect races. In Java, there's link check. Some framework to verify data structures. But unfortunately, the answer is more negative because if your test fails, it means there's a problem. But if your tests complete successfully, it's not a guarantee that everything's fine. So the past test does not guarantee that you don't have race. So unfortunately, this is the way it works. Thank you very much for your questions. Sasha, now the most difficult question for you. Who you're going to award the girl that asked about quantum computer? I think that was an out-of-the-box question, so let's award the book to her. So please come to us, and thank you very much for your presentation.